Look at your hand. You can see it, right? Which means light is bouncing off it, traveling through space, entering your eye and triggering a cascade of chemical reactions that your brain interprets as vision. Simple. Except here's the problem. Nobody knows what light actually is. Not in the way you might think. We know what it does. We know how to manipulate it, measure it, use it. We've built entire civilizations on our ability to control light. But when you ask the question, what is light fundamentally? The answer gets deeply, uncomfortably strange. Because light is somehow both a wave and a particle. It travels at a speed that nothing in the universe can exceed. And that speed, 299,792,458 meters per second, isn't arbitrary. It's built into the structure of space-time itself. By the end of this lecture, you'll understand what light actually is, why it behaves the way it does, and why the speed of light isn't really about light at all. My name is Dr. James Mitchell, and this is Science Explained Properly. Let's begin. For most of human history, light was just light. You couldn't touch it, you couldn't hold it, but you could see by it, and that was enough. The ancient Greeks thought light was something that emanated from the eyes. That vision was an active process, like reaching out and touching things with invisible rays, which, if you think about it, is a perfectly reasonable guess if you don't have any way to test it. But eventually, people started doing experiments, and the experiments revealed something strange. In the 1600s, there was a debate. Isaac Newton, yes, him again, thought light was made of particles, tiny, discrete packets that shot out from sources like cannonballs. His reasoning was solid. Light travels in straight lines, casts sharp shadows, and reflects off surfaces like bouncing balls. Particles. But Christian Huygens, a Dutch physicist, disagreed. He thought light was a wave. Because waves do something particles don't. They interfere with each other. If you send two water waves toward each other, they create patterns, peaks combining with peaks, troughs cancelling out peaks. And light does that too. If you shine light through two narrow slits, you don't get two bright spots on the wall behind them. You get a pattern, an interference pattern, alternating bands of light and dark, exactly like what you'd expect from overlapping waves. So Huygens was right, and Newton was wrong. Light is a wave, case closed. Except, not quite. Because in the early 1900s, physicists discovered something that waves absolutely should not do. Here's the experiment that broke everything. Shine light on a piece of metal. Under the right conditions, the light knocks electrons out of the metal. This is called the photoelectric effect. And at first glance, it makes sense. Light is energy. Energy hits the metal. Electrons absorb that energy and escape. Simple. But here's the problem. If light is a wave, then increasing the brightness, or the intensity of it, should give the electrons more energy. Brighter light equals more energetic electrons. But that's not what happens. What actually happens is this. The energy of the ejected electrons depends on the color of the light, not the brightness. Blue light ejects high-energy electrons. Red light ejects low-energy electrons. And if the light is too red, if the frequency is too low, then no matter how bright you make it, no electrons come out at all. That makes absolutely no sense if light is a wave. Waves don't care about color in that way. A big wave and a small wave deliver energy differently, but both can deliver it. But light was acting like it came in discrete packets. Packets that either had enough energy to kick out an electron or didn't. Like particles. In 1905, Albert Einstein proposed a solution. Light isn't purely a wave. It also behaves like a particle. He called these particles photons. Each photon carries a specific amount of energy determined by the light's frequency. High-frequency light, like blue and ultraviolet light, equals high-energy photons. Low-frequency light, like red and infrared light, equals low-energy photons. And you can't split a photon. Either it has enough energy to knock out an electron, or it doesn't. Brightness doesn't matter. It just means more photons, not more energetic ones. Einstein got the Nobel Prize for this, not for relativity, for figuring out that light is also made of particles, which brings us to the deeply uncomfortable question: how can light be both a wave and a particle? Well, let me describe an experiment to you. It's one of the most famous experiments in all of physics, and it's deeply, genuinely unsettling. Take a barrier with two narrow slits cut into it. Shine light through the slits onto a screen behind them. If the light is made of particles, you'd expect two bright lines on the screen, one behind each slit. But that's not what you see. You see an interference pattern, alternating bright and dark bands, waves interfering with each other. Okay, fine. Light is a wave. Now do the experiment again, but this time turn the light down so low that only one photon passes through at a time, one particle at a time. Each photon should go through one slit or the other, hit the screen, and create a dot. Over time, you'd expect two clusters of dots, one behind each slit. But that's not what happens. The dots slowly build up into the same interference pattern, the same alternating bright and dark bands, as if each individual photon is somehow interfering with itself. Now here's where it gets truly strange. Set up a detector at the slits, something that tells you which slit each photon goes through. You'd think this wouldn't change anything. The photon still goes through one slit or the other slit. It still hits the screen. But the moment you measure which slit the photon goes through, the interference pattern disappears. Suddenly, you get two clusters of dots. The act of observing changes the result. Let me say that again. When you're not looking, photons behave like waves and create an interference pattern. When you are looking, when you measure which slit they go through, they behave like particles and go through one slit or the other. The universe behaves differently depending on whether you're watching. This isn't philosophy. This isn't interpretation. This is what the experiment shows every single time. And nobody has a completely satisfying explanation for why. At least not yet, anyway. So, what is light? Is it a wave? Is it a particle? The honest answer is both, and neither. Light is something more fundamental than either waves or particles. It's a quantum object. And quantum objects don't fit neatly into the categories our brains evolved to understand. Here's the best way I can describe it. Light is a disturbance in the electromagnetic field. The electromagnetic field is everywhere. It fills all of space. When that field oscillates, when it ripples, that ripple is what we call light. At large scales with many photons, it looks like a wave. Smooth, continuous, predictable. At small scales with individual photons, it looks like particles. Discrete, localized, countable. But fundamentally, it's neither. It's a quantum field excitation, which is a fancy way of saying it's something our everyday language doesn't have words for. Think of it like this. Imagine you've never seen a coin, and I try to describe one to you using only the words flat and round. Depending on which angle you look at it from, the coin appears flat, edge on, or round, face on. But the coin itself isn't flat or round. It's a three-dimensional object that can appear flat or round, depending on your perspective. Light is similar. Wave and particle aren't what light is. They're how light appears when we measure it in different ways. The underlying reality is something deeper, something quantum. Now let's talk about the speed of light. 299,792,458 meters per second, often rounded to 300,000 kilometers per second, or about 186,000 miles per second. It's fast, really fast. It's actually fast enough to circle the Earth 7.5 times in just 1 second. But here's the question. Why that speed? Why not faster? Why not slower? Why is the speed of light what it is? Here's the uncomfortable truth. The speed of light isn't about light. It's about the structure of space-time itself. It's the maximum speed at which cause and effect can propagate through the universe. Let me explain what that means. Imagine you're sitting here and I'm standing 10 meters away. I clap my hands. The sound reaches you a moment later. It takes about 0.03 seconds because sound travels at roughly 343 meters per second through air. But the information that I clapped, the cause and effect relationship, can't reach you faster than the sound does. There's a maximum speed at which information can travel. For sound, that speed is set by the properties of air. For light, for anything in the universe. That speed is set by the properties of space-time itself. And here's the key insight. Light travels at the maximum possible speed because photons have no mass. Anything with no mass always moves at the maximum speed allowed by space-time. That speed is what we call the speed of light. But really, it's the speed of causality, the speed at which the universe updates. Now, what about things with mass? If you have mass, you can't reach the speed of light. Not because there's some cosmic speed limit sign, but because as you accelerate closer and closer to the speed of light, something strange happens. Your mass effectively increases. The faster you go, the more energy it takes to accelerate you further. To reach the speed of light, you'd need infinite energy, which you don't have, so you can't get there. Only massless things, like photons, travel at the speed of light. Everything else goes slower. Here's something beautiful. Light isn't just light. It's the connection between electricity and magnetism. In the 1860s, James Clerk Maxwell was working on the mathematics of electricity and magnetism. He'd written down a set of equations, now called Maxwell's equations, that described how electric and magnetic fields interact. And when he solved those equations, something extraordinary fell out. A wave, a self-sustaining wave where an oscillating electric field creates an oscillating magnetic field, which creates an oscillating electric field, and so on. The two fields leapfrog through space, sustaining each other. An electromagnetic wave. And when Maxwell calculated the speed of that wave, he got a very specific number. 299,792,458 meters per second. The speed of light. Maxwell realized in that moment what light actually was. Light is an electromagnetic wave. Visible light, the narrow band of frequencies our eyes can detect, is just one small part of the electromagnetic spectrum. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays are all the same thing. Electromagnetic waves, just at different frequencies. Your Wi-Fi, electromagnetic waves, your microwave oven, electromagnetic waves. The warmth you feel from the sun, electromagnetic waves. X-rays at the hospital? Yes, electromagnetic waves too. All of it is light in the broader sense. All of it travels at the speed of light. All of it is a ripple in the electromagnetic field. Let's bring this back to something personal. Vision. You're watching this video lecture because light is entering your eyes. But what's actually happening? Photons are bouncing off surfaces around you. Some of those photons happen to travel toward your eye. They pass through your cornea, through the lens, and hit the retina at the back of your eye. The retina is covered in light-sensitive cells, rods, and cones. When a photon hits one of those cells, it triggers a chemical reaction. That reaction sends an electrical signal down your optic nerve to your brain. Your brain processes millions of these signals and constructs an image. That's vision. It's photons, absorbed by cells, converted into electrical signals, interpreted by your brain. Now here's the strange part. The photon that just hit your eye and allowed you to see, that photon doesn't exist anymore. It was absorbed. Its energy was converted into a chemical reaction. It gave up its existence so you could see. Every photon that enters your eye ceases to exist in the process of letting you perceive the world. Vision is the destruction of light. And here's something even stranger. The photons entering your eyes right now, some of them might have been traveling for millions of years. If you look at a distant star, the light you're seeing left that star long before you were born. You're seeing the past, not metaphorically, literally. The universe has a speed limit, and because of that, looking out into space is looking back in time. When you see the Andromeda galaxy, you're seeing it as it was 2.5 million years ago. Because that's how long it took the light to reach you. Let me end with this. The speed of light isn't just a number. It's not just a physical constant. It's the speed at which reality propagates. If the sun suddenly disappeared, just vanished, we wouldn't know for 8 minutes, because that's how long it takes light to travel from the sun to Earth. For 8 minutes, we'd still see the sun in the sky. We'd still feel its warmth. We'd still orbit the space where it used to be. Because information, including gravitational information, can't travel faster than light. Nothing can. And that has profound consequences. It means the universe is fundamentally local. What happens here can't instantly affect what happens there. There's always a delay, a light speed delay. Cause and effect are separated by distance and time. And that separation, that cosmic speed limit, is what gives the universe structure. Without it, causality would break down. Events could happen in different orders depending on your perspective. The universe would be fundamentally incoherent. The speed of light is what makes reality possible. All right, let's bring this together. We started with a simple question: what is light? And what we've found is that light is something far stranger than a simple answer allows. It's both a wave and a particle, and neither. It's a disturbance in the electromagnetic field, a quantum object that doesn't fit into our everyday categories. It travels at the maximum possible speed through spacetime, not because light is special, but because that speed is built into the structure of reality itself. It connects electricity and magnetism. It allows you to see, and it sets the cosmic speed limit for cause and effect. But here's what I want you to sit with. Right now, photons are entering your eyes. They've traveled, some of them, across unimaginable distances. They've survived the void of space, the chaos of Earth's atmosphere, the journey through your cornea and lens. And in the final moment, when they reach the cells at the back of your eye, they cease to exist. They give up their existence so you can see. Every moment of vision is the end of a journey for countless photons. Photons that might have left a star 1,000 years ago. Photons that might have bounced off a face you love. Photons that carry information about shape, color, distance, and time. And they all travel at the same speed. The speed that defines the structure of space-time. The speed which separates cause from effect. The speed that makes the universe comprehensible. You are seeing the universe at the speed of light. Every photon that reaches you is a messenger that traveled at the maximum possible speed to bring you information about the world. And in the act of delivering that message, it ends. You are surrounded by light. Light that connects you to everything. Light that allows you to see. Light that defines the very structure of reality. In a future lecture, we'll explore energy. Not the vague, everyday use of the word, but what energy actually is. One of the most fundamental and misunderstood concepts in all of physics. But for now, look around, see the light, and remember, every photon that reaches you traveled here at the maximum speed the universe allows, just to let you see this moment. Thank you for listening. I'll see you in the next lecture.